All right, here we go. Lesson 10.7. This is regarding inscribed and circumscribed. So here we go. Fancy terminology. First one, inscribed. What does it mean to be inscribed? Well, to be inscribed in a circle, yes, in this case here, we have a triangle is inscribed in the circle. All right? So the circle touches the triangle specifically only at the vertices. All right? Now, you could flip this around and say the circle circumscribed is circumscribed. The triangle is circumscribed by the circle. All right? So it's either an inscribed triangle or the triangle is circumscribed by the circle. It depends upon how you want to phrase it. So let's look at this second definition. Again, to circumscribe means to go around something, and we touch it once on each side, so to speak. So again, notice in the inscribed nature, again, I shouldn't use inscribed, right? Sorry about that. I should say something like to be inside, but vertices touch the circle. Okay? Whereas circumscribes to go around something, and you are tangent. All right, so the circle in the second example is circumscribed by the triangle. All right? So try to keep those two words separate. Now then we can talk about the circumcenter and the in-center. All right? So what is a circumcenter? So the circle, again, is on the outside. The circle with a center A is circumscribed around a polygon. Where is the circumcenter? This is something that we're going to be talking about in the future. It's important to find the circumcenter of this polygon, and to do that, we construct perpendicular bisectors of each side, and those perpendicular bisectors will each intersect at a spot known as the center of the circle. And again, what is it called? It's called the circumcenter. This is not to be confused with the in-center. So this is now the circle inside. So notice here the circle was on the outside. So here again I've got a pentagon, just like in the last example, only instead of touching, the vertices, I'm now tangent on the inside. All right? In this case, we're going to draw from each point of tangency, we draw the perpendicular. Yes? So it isn't a bisector, it's just the perpendicular. And those two, yes, will meet at a spot. And that spot will be the center of the circle, so to speak, of that circle. All right? So the polygon is circumscribed around the circle with center B. I can also find an in-center using a triangle, for example. Draw a circle in the middle. Again, pick those spots where they're tangent and draw the perpendiculars to the tangents. And they will meet at the spot known as the in-center. All right. In a inscribed, a little funny how I pronounce that, inscribed quadrilateral, we have angles that are opposite. right? So if you have a circumscribed quadrilateral, notice the circle is on the outside, yeah? Then the opposite angles are supplementary. So this is a handy theorem. Get this one down. Even you might want to use that name, Inscribed Quadrilateral. So how do I know that they will be supplementary? How do I know that they're going to add up to 180? Well, notice these two arcs which have been highlighted. Yes? So angle A intercepts this arc. Angle B captures this arc. Oh, notice that's 360. And because the angles are half, right? So the measure of the measure of angle A is equal to 1/2 of the arc it intercepts. And then the measure of angle B is 1/2 the arc of the other arc. Well, these two arcs add up to 360, then half of that is 180. So that means these two angles here will add up to 180. All right? I should have some M's in front of there. All right. Last thing I want to highlight here is another little proof. I'm not going to go through the detailed end of the proof, but if you have a circle and you have inscribed a parallelogram, then guess what? You've inscribed a rectangle. All right? So if you put a parallelogram, now let me try drawing a parallelogram that is not a rectangle in a circle. All right, so there's a nice circle, and if I try to draw, let's say, a parallelogram, there's my opposite angles, right? And let's say I go up to here. Notice what I immediately, well, no. Okay, let's try this. All right, there I've got a 90, not a 90. That angle there looks like it's opened up more. Now if I draw a parallel line, I'm going to run into trouble. I can't fit it. Okay, so the rule is that as soon as you put a parallelogram and you inscribe it, guess what? That parallelogram has to turn into a rectangle. I wish I could take this point here and stretch it, but then eventually this thing would, if it's a parallelogram, opposite sides are parallel, then it would have to be a rectangle. All right, and I think the way I would prove that is if you draw a shape like this, and then you prove to yourself that, well, we know opposite angles are congruent, right? That's something that we studied in the past, so that angle and this angle are congruent. All I need to show then is that this angle and this angle are the same, and then I would know that all angles are congruent. So I would just then prove that this triangle is congruent to this triangle. And that is pretty easy to show. The tricky is to show that this is congruent to this. But it's not difficult to do that. But like I said, I'm not going to bore you with those details on that proof. Know that when you do have this theorem, you can identify the diameters. You can identify the center of the circle, right? And you can identify all these radii. So let's go back here, right? Bam, parallelogram inside a circle. Guess what? It's a rectangle. Therefore, boom, boom. Therefore, there I've got the center, right? These are radiuses. These are all 90 degrees. Okay? All these things happen. All right, that's it. 10.7 is done. We review tomorrow, test on Friday.